Let's continue on chapter 11, section 7. Is a combination of all those strategies that we've learned at the moment to discuss convergence or divergence of a series. So I've written down some of these. It's not really an order that you need to go through, but generally speaking, this is what we would check if we were trying to find out a divergence or convergence based on the strategy. It doesn't mean that you start from step 1, step 2, and 3, but these are necessary to know if you're trying to figure out convergence or divergence of a series. So first of all, we know that if we have a summation of 1 over n to the power of p, it is convergent if p is greater than 1, otherwise it's divergent. So this is a p-series test. We already know this from the earlier sections. Convergent if p is greater than 1, divergent otherwise. And similarly, we dealt with if we are dealing with a geometric series, it is convergent if absolute value of r is less than 1. Otherwise, we're dealing with divergent. These are necessary because when we use comparison test, quite often we end up with either using p-series or geometric series to compare it. So the third idea is to discuss the comparison test. So when do we use comparison test? You look at the sequence and what is the format of that sequence. Normally, if it's a rational function, generally speaking, or an algebraic function without the nth power, so there is no exponent of order n. So if you have n, for example, n to the power 3 or n to the power 2 divided by another, so if it's in terms of a geometric or rational fraction, you kind of wanted to use comparison test. And how do you apply the comparison test is you pick the largest term. If you're dealing with fraction, you pick the largest term in the numerator, largest term in the denominator. That would be a good indication to use comparison test. If we, for example, if we're dealing with some constant to some power, then in that case, maybe geometric would be a better comparison. Geometric would be a good option to use for comparison. And we know one thing that if the limit of an's are not approaching 0, that's definitely the series would be definitely divergent. So this is quite important that you check for this maybe at the very beginning to see if there are indications that maybe an's are not approaching 0, then you can simply say the series divergence. You don't need to go through the process of figuring out, can I compare it to another test, can I use ratio or root test or any other combination. So this number 4 maybe is very useful if an's are quite easy to see if they're approaching 0 or not. If we're dealing with alternating series, we have the alternating test. That's a powerful test. It tells you the series convergent or divergent. And if our series involved factorial or some other powers, some constant to some powers, where the powers are not really constant, the powers are some variables, then ratio test is quite often used. If you see factorial, here is the important part, if you see factorial, about 90% of the time the ratio test is a good choice. If you see nth power somewhere, where bn already is not a constant, if it's like a variable also, and bn is a sequence by itself and to some power n, then in that case the idea would be to use root test, because you want to get rid of the power, at least this nth power, and say, okay, now I can discuss what does bn behave. And finally, if an could be approximated by a function f of n, and that f of n is decreasing and satisfies the properties for the integral test is quite often useful if you can really integrate this integral. So if f is not super complicated, maybe you can use this integral test. Okay, so these are strategies, and again, as I mentioned, there is no ordering. It doesn't mean that you have to check 1, 2, 3, 4. It's just basically you look at the structure of the sequence and the series and decide based on that which one would be a better choice. Not always you'll pick the right choice right away. So here I wrote down a bunch of examples. We can go through these examples together. So first example, you have n minus 1 divided by 2n plus 1. Always check to see if the series really, so here an, what is an? An is n minus 1 divided by 2n plus 1. Ask yourself that, is this really true? If limit an as n approaches to infinity, do we get 0? Because if we don't get 0, there is no need for me to continue, right? This is required to discuss convergence at least. If this is not 0, we could simply say divergence. So I'm gonna, most of the time, I will look at the series, I will look at the sequence an, and if I see an is not converging to 0, I can simply say divergence. So in this case, I could have looked at this sequence and say, okay, let's ignore these constants. What do I have as a ratio is 1/2. So the limit n minus 1 divided by 2n plus 1 as n approaches to infinity. In this case, it simplifies to really limit n divided by 2n as n approaches to infinity. Because the other terms are simply will cancel out if you divide by n everywhere. And this is 1/2. You can take a Hopital rule here and say that you will end up with 1/2. You don't really need to write this step down. This is just to show you the idea of how do they say maybe you try this. Okay, so if the limit is 1/2, then I can say series divergence. So maybe I should say summation of an's divergence. Okay, so in this case, I didn't really start from number 1, I started from number 4. Because it was required to find out if the limits are approaching 0 or not. Some cases, so that was it for that case. In some cases, it's not that easy. So if I look at this, is it that easy to see if the limit converges or not? Most often, if you're dealing with fraction, just pick the largest terms and see how they behave. So here, in the largest term, it's n cubed, in the numerator with the square root. The denominator is 3n cubed. I can kind of see that this is similar to n to the power 3/2 divided by 3n to the power 3. This is, I'm picking the largest term in the numerator and denominator. And ratio-wise, what do I have is n to the power 3/2 divided by n to the power 3 is 1 divided by 3n to the power 3/2. I can simplify. And now I say if I let n approach to infinity, what happens is an will approach 0. So I wouldn't have the difficulty that we had in the last case. And now that I end up with this simplified version of the largest power, I can kind of say, let's use comparison test. Maybe I should say limit comparison test. And I'm going to pick Bn to be basically this limit. 1. You can ignore the 3's also. This is not really necessary. N to the power 3/2. This is what I pick for Bn. Why do I pick this? Because now if you remember in the limit comparison test, what we really need to do is to show that if I have limit, so now I pick the Bn's to be that. So I need to calculate limit an divided by Bn. If this was a constant, if this was some constant, then however Bn behaves, summation of Bn behaves, summation of an's will behave the same way in approaches to infinity. So in this case, as we know, an, change this, an is simply square root of n cubed plus 1 divided by 3n cubed plus 4n squared plus 5. So if you're dealing with algebraic or fractions, normally this is the idea. You use the limit comparison test. And then you calculate the limit. What is the limit? Limit absolute value is not necessary. So here we have square root of n cubed plus 1 divided by 3n cubed plus 4n squared plus 5 divided by 1 divided by n cubed. 3/2 as n approaches to infinity. You can simplify this. You can multiply that to the numerator, limit n to the power 3/2 is basically, this is n square root of n. Or you can write it as n cubed square root. Right, so if I multiply that to the numerator, it becomes n cubed times n cubed. So it becomes square root of n to the power 6 plus n cubed times 1 becomes n cubed. And here in the denominator you have 3n cubed plus 4n squared plus 5 as n approaches to infinity. And what can you say about this? You can pick the largest, you can divide everything by n cubed just because n cubed is the largest. And n cubed under the square root basically would be n to the power 6. So I can say this is the same as limit dividing everything by n cubed, n to the power 6 plus n cubed. Let me show you what I mean. I divide an n cubed everywhere. 4n squared plus 5 divided by n cubed as n approaches to infinity. And now I can put this n cubed inside the square root and make it square root of n to the power 6. Because square root of n to the power 6 is basically n cubed. And then this would be n to the power 6, n to the power 6. I can write this separately underneath each one, n cubed, n cubed, n cubed. And I'm doing this just because I don't have enough space. I should have created more space. Otherwise, you should write it step by step, just to make sure you don't make any mistakes. And then the numerator simplifies to square root of 1 plus 1 divided by n cubed, divided by 3 plus 4 over n plus 5 over n cubed, as n approaches to infinity. As n approaches to infinity, what happens? This is 0, this is 0, this is 0. So what do I end up with is simply 1/3. And then what can I say? I can say, since the limit an divided by bn ended up to be a constant, I can say, however summation of bn behaves, summation of an will behave the same. Behave similarly. But what do I know about summation of bn? Summation of bn, which is 1 divided by n to the power 3/2, is convergent. How do we know that? From the p series. Here p is the power of n 3/2, greater than 1, so it's convergent. So if this is convergent, that means summation of ans was convergent. That means this series converged. Okay, so quite often, if you're using this, I should say here maybe use limit comparison test. Use limit. So quite often, if you're using limit comparison test, basically you're picking the largest terms in the numerator and denominator to create that bn. So this bn was created by doing the largest term in the numerator and denominator. Okay, here's another example. N e to the power negative n squared. Ask yourself, can I use bn here? What would be bn if you're trying to use comparison test? Because there is no, you can pick the fraction. You can write this in terms of fraction, by the way. You can write this as summation n divided by e to the power n squared. But it doesn't give you anything because the largest terms in the numerator and denominator are already there. So the comparison test may not be very useful. And if you let n approach to infinity, then this would approach to 0, but you have to use Hopital rule. But in that case, then you're showing that the limit an as n approaches to infinity, I should say limit n divided by e to the power n squared as n approaches to infinity. Try to use Hopital rule, you will see that this is 0. You'll end up with 1 divided by infinity. If you take the derivative of the numerator, it becomes simply 1. Denominator would still have e to the n squared. So you'd have this limit. And it doesn't tell you that if the series converges or diverges. So this doesn't tell you any information about divergence. But what can you see is basically that every time you're dealing with e to the power negative n, everything in this format, is always a decreasing sequence, because if you remember, exponential looked like that. This was e to the power n. If I change it to e to the power x, if I change it to e to the power negative x, it kind of becomes a decreasing function. If you remember, for the decreasing function, what we needed basically to show that the area under this series is convergent, or the area under this function is convergent, then in that case we could have said the series is convergent. So maybe the best choice would be to compare this using the integral. So I use the integral test. Right, this was using the integral test. Because now I can see that I can calculate that integral quite easy. What is the integral from 1 to infinity of x, the function that we pick is x e to the negative x squared dx. And you can use a substitution. I'll let u equal negative x squared, du would be negative x, negative 2x dx. Therefore, I can find out that du divided by negative 2x is dx. You can update the boundaries. By the way, if I let x equal to 1, then u would become negative 1, so u would be negative 1. And if you pick x to be infinity, then u becomes negative infinity. So this is basically from negative 1 to negative infinity. Or you can calculate the integral and update the boundary. Up to you, however you want to calculate. X times e to the power u times, instead of dx, what we have is du divided by negative 2x. Right? So I can cancel out the x's, and basically what we have is integral from negative 1 to negative infinity e to the power u d. There is a negative 1/2 outside. Okay, so this integral, what is the integral? The integral will be e to the u, negative 1/2, evaluated from negative 1 to negative infinity. You can use a limit, so it will be limit negative 1/2 e to the u, as u approaches to negative infinity, minus, if we replace negative 1, you get negative 1/2 e to the negative 1. And this simply becomes e to the u, as u approaches negative infinity, it becomes 0, so you get 0 minus 1/2 e, it becomes 1/2 plus 1/2 e to the power negative 1, which is 1/2e. Okay, so what do we get? We get that the integral is convergent. So the integral is bounded, evaluated. We can calculate this integral. So by the integral test, I can say the series of n e to the power negative n squared from 1 to infinity is convergent. And why was that? That was because the integral existed. If the integral didn't exist, then we could have said the series divergent. Okay, so this is, again, it doesn't follow the order. The question is, what do you see would be useful to, which strategy would be useful? That's the idea. You look at the series and you pick based on that. Okay, here is another example. Convergence or divergence of this series. The moment that you see this negative 1 to the power n, you kind of have to get rid of that. You kind of have to check, what can I do with this? And most often, if you're dealing with fractions without the nth power or n factorial involved, the best choice of action is simply alternating test. This is the best choice of action when you see this negative 1 to the n power. Okay, so what you need to check is, first, is n cubed, because we have, for the alternating test, we needed to figure out the behavior of this Bn, which was n cubed divided by n to the power 4 plus 1, basically without that n, negative 1 to the power n. We just needed to find out if this is this decreasing, and also, does the limit Bn as n approaches to infinity, is that 0 or not? If we show these two, then we can say the series would be convergent. If we couldn't show one of them, then we can say the series is divergent. So basically, we need to figure out this. And how do we find out the decreasing? You take a derivative, you look at the behavior. So the derivative would be denominator squared. Again, you can change this to x, but I'm assuming n is continuous for the moment when I'm taking the derivative. 3n squared times n to the 4 plus 1 minus n cubed times 4n cubed. And as a simplification, I can find out that this is 3n to the 4, n squared times n to the 4 is 3n to the 6. So I'll get negative n to the 6 plus 3n squared. And divided by n to the 4 plus 1 squared. And you can factor out an n squared in the numerator just to see it more clearly. You'd have n to the 4 plus 3 divided by n to the 4 plus 1 squared. The moment that we let n to be 2 and larger, this term is always negative. So this becomes negative. Negative times a positive becomes negative. So in the numerator, you would have a negative number. The denominator is always positive. So negative divided by a positive, it gives you a negative value. That means that this is a decreasing series. So this decreasing is true. And does the limit approaches 0? So let's calculate the limit. Limit n cubed divided by n to the power 4 plus 1. As n approaches to infinity. You can use the Hopital rule, or you can divide by n cubed, however you want to do it. 3n squared divided by 4n cubed. As n approaches to infinity, you can simplify n squared, will cancel out the 2 of these guys. So you'd have limit 3 divided by 4n as n approaches to infinity. And that is 3 divided by infinity is simply 0. So this is also a true state. Okay, both of these two are true, and I can say this is a convergent series by the alternating test. Okay, so quite often if you deal with this negative 1 to the nth power, alternating test would be a good choice if you're not really dealing with n to the power n, for example, or n factorial, because taking the derivative of those to figuring out if it's increasing or decreasing, it's going to be a tough thing. So here, as I mentioned, when you notice is we're dealing with factorial. Also, we're dealing with powers of n. So n factorial to the nth power divided by n to the 4 nth power, 4 to the nth power. If this is the maybe I should say here. If you're dealing with nth power, first figure out if you can write everything in terms of one fraction or one function to the all to the nth power. So for example, can I write this as n factorial divided by n to the power 4, the whole thing to the n power? I can do this. This is the same series. N to the power n factorial to the power n divided by n to the 4 to the power n. N to the 4 to the power n is basically the same as n to the 4n. This is the same as the denominator. I just wrote it this way so you can show you that this is exactly the same. If you could do this, if you could write to one term, one series to the power n, in these cases, the best choice of action is the root test. I'm not saying that always is going to work out, but most of the time that's the case, because you can write it in terms of one series, you can write the an in terms of a sequence to the power n separately. Okay, so if that happens, maybe root test is always the best choice. So what is the root test? If you remember, we need to calculate limit the nth root of absolute value of an as n approaches to infinity. And based on the result, if that result is less than 1, we would say convergent. If it's greater than 1, we would say divergent. If it's equal to 1, then it's conclusive and we have to use a different idea. So let's calculate this limit. An in this case is positive, so I don't really need the square root. the absolute value. So here nth root of an, which is n factorial, divided by n to the power 4, the whole thing to the power n. As n approaches to infinity, what you get is limit. The nth and nth root will cancel out, so you'll end up with n factorial divided by n to the power 4, as n approaches to infinity. Here's the one thing that you should know. What do you know about the ratio of these two? So the question basically becomes, how do we figure out what is this limit? Because it's quite difficult to see at the moment. Well, let me show you. So now we want to figure out what is this limit. So let me show you something. I'm going to show you with the numbers, then we can extend it. Same idea. So let's say you want to replace n with 1. What happens? You have n factorial divided by n to the power 4. Let's calculate for different n's. So I'm going to calculate for different n. If n equals to 1, what happens? You get 1 factorial divided by 1 to the power 4, simply 1. If n equals to 2, you get 2 factorial divided by 2 to the power 4, that is 1 over 8. N equals to 3, you get 3 factorial divided by 3 to the power 4, becomes 6 divided by 3 to the power 4, that is 2 over 27. Okay, let's say we calculated a bunch of them, and then now we have n equal to 10. Okay, here is the important part. In the numerator you have 10 factorial, in the denominator you have still 10 to the power 4. 10 factorial is 1 times 2 times 3 times 4 up to 10. Denominator would be simply 10 to the power 4 means 10 times 10 times 10 times 10. You can cancel out one of these 10s. So you have 3 10s in the denominator, and product of 1 to 9. 1 times 2 times 3 times 4 times 5 times 6 times 7 times 8 times 9 divided by 10, 10, and 10. Okay. Ask yourself, is this number greater than 1 or less than 1? You can cancel out 2 times 5 is 10. I can cancel out with one of these 3. 3 times 4 is 12. At least it is 10. So this is 3 times 4 is larger than 10. It's greater than one of these denominators. 6 times 7 is 42. It's greater than this 10. So I can say, let's cancel out all these with one of these 2 10s. What is left is still 9 times 8. So definitely this is greater than at least 60. 9 times 8 is 72. So this is at least greater than 72. At least. It is definitely larger. So what can I say is, as I pick the n to be larger and larger, what happens is that the fraction becomes larger and larger as well. Just because I can say this simplifies to basically calculating the limit of 1 times 2 times 3 times n minus 2, and maybe I should write n minus 3, n minus 2, n minus 1, and all divided by n to the power 4. And what is n to the power 4? N to the power 4 is times n times n times n. As n approaches to infinity, what happens is these two can cancel out. This is almost the same ratio as that. This is almost the same ratio as that. This one is almost the same as that. And you're left with all these terms multiplied by each other. As n approaches to infinity, this is very large and it becomes infinity. The idea is, what you need to calculate here is just to see that this is an increasing function. It's not really decreasing. Taking a derivative is not that often accessible because the derivative of n factorial is not that easy to calculate. But as I know that this is quite getting larger and larger, I can say this limit of square root of the nth root of absolute value of n, this is infinity. If that's the case, then this series is divergent. Okay, so this is quite important to calculate throughout this process. How about this one? Summation n from 1 to infinity to the power n divided by n factorial. Notice that in this case, only the numerator has power n. The denominator doesn't have an n power. Best choice of action in those cases is to use the ratio test. Ratio test is if you're dealing with n factorial with any n power. If you had to the power n, then maybe nth root would have been a better choice. Okay, so by the way, here is one hint maybe I should mention. Note limit n factorial divide by n to any power, any constant power. As n approaches to infinity, is always infinite. The numerator, when you're dealing with factorial, divide by n to any constant power is always infinite. You can use this when you're calculating the limit. Let's accept it for the moment. And that would be quite useful if we're dealing with ratio tests when you cannot calculate the derivative. Okay, so let's do this example as well. So in the ratio case, what we needed to calculate, if you remember, we needed to calculate limit absolute value of an plus 1 divided by an as n approaches to infinity. If this was some constant greater than 1, divergence, less than 1, it would have been convergent. If it equals to 1, then we would say this test is inconclusive and we have to come up with a different idea. So let's calculate this limit. Limit an plus 1. By the way, everything is positive, so absolute value is not necessary. N plus 1, an plus 1 would be 2 to the power n plus 1 divided by n plus 1 factorial divided by 2 to the power n over n factorial as n approaches to infinity. And in this case, we can simplify it. You can cancel out 2 to the n with 2 to the n, and in the numerator, this will be left with 2 to the power 1 left. So basically, you have 2 to the power 1 multiplied by n factorial divided by n plus 1 factorial as n approaches to infinity. Okay, so if you remember in the last section, I already simplified some of these. And if you don't remember, it was if you're dealing with factorials divided by each other, you can write them out. This is this 2 still there. N factorial would be 1 times 2 times 3 times 4 up to n. And in the denominator, you have n plus 1 factorial, which is exactly the same thing, except there is an extra term, n plus 1. It's 1 to n plus 1 as n approaches to infinity. These terms can cancel out with each other. So this ratio is simply 1 n plus 1 left in the denominator. Okay. So what is the simplified version? The simplified version is 2 divided by n plus 1. As n approaches to infinity, this limit basically becomes 0. So what we can say? We can say that this is less than 1 as the result. So this series is convergent. If that number was something like 3 greater than 1, then you would assert divergent. If it was 1, then it was inconclusive. In this case, it's 0 less than 1. Okay, so I hope this clarifies at least some strategies to use for convergence and divergence of the series. It's not always common that you use this tests, but most of the time they're quite useful. I'm going to stop here. Next time we'll continue on 11.8.